All right, in this video, we're going to go over our factorial notation and summation notation, two very important concepts. So when you see this exclamation point in math, it doesn't mean we're really excited. It means that we are going to do what's called a factorial. So the factorial of a number is that number times the number that is one less than it, times the number one less than that, and so on. So I think it's easier to look at this example first. 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1, or 5040. We could be general and say that the factorial of n, any number, is that number times that number minus 1 times the original number minus 2, and so on. All right, something that is kind of maybe counterintuitive is 0 factorial is equal to 1. It seems like it should be 0, but it's not. It's equal to 1. Just to show you, in your graphing calculators, there is a way to evaluate factorials in your calculator. You type the number that you want to find the factorial of, you go to math, and you go over to probability, and it's the 4th option down. And then you just hit enter, and there you go. 5040, just like in that box. All right, in example 1, we don't need the calculator for either of these examples. We just need a little bit of logic. So if I want to evaluate this, there's a way to do this without having to multiply 30 times 29 all the way down to 1. So let's think about this. 30 factorial is the same as saying 30 times 29 times 28 times 27, and then I'm going to keep going. But if I keep going, that's the same as saying 27 factorial. The reason I'm stopping at 27 is I notice my denominator is 27 factorial. So these are everything in a factorial is multiplication. So because these are all factors, we can cancel out 27 factorial from the numerator and denominator. So now we just have to multiply 30 times 29 times 28. Plug that into your calculator. You should get 24,360. All right. For example 2, we're asked to simplify n plus 2 factorial over n factorial. Don't let this intimidate you. N plus 2 factorial. And also, don't try to distribute that factorial or anything like that. You can't do that, so don't try to use the distributive property when you see that. But n plus 2 factorial is going to be n plus 2 times n plus 2 minus 1. Well, n plus 2 minus 1 is just n plus 1. All right, times n plus 1 minus 1, which is just n. And as we keep going, I'm going to be multiplying next by like n minus 1, n minus 2, n minus 3. That's the same as n factorial. So from there, if that's my numerator and n factorial is in my denominator, they're all factors, cancel them out. I should say divide them out because n factorial divided by n factorial is 1. So our final answer is just n plus 2 times n plus 1. All right. You also need to be familiar with summation notation. You'll see this a lot in calculus, especially Calc 1, I do believe. Summation notation. This capital sigma, the Greek letter sigma, is the symbol for a summation. It's going to tell us what to add up, where to start, and when to stop. So for example, if I had this sequence, or we could think of this as a sequence, we might not be given a sequence, but if I had this sequence of numbers starting with the first term all the way to the nth term, I'm going to start when my lower limit is starting at the first term. I'm going to add everything up till I get to the nth term. So I could think of this as the sum of a sub I as I goes from 1 to n. The letter I is used to represent the index of the summation, and the index is like that starting point or lower limit. N will tell you where to stop. That's the upper limit. So you're going to add from here to here. These look a lot scarier than they are, but they can be really intimidating. Let's look at this first example together. So we're asked to evaluate the summation of n factorial over 2 from n equals 1 to n equals 5. That's not too bad. So we're going to start at 1. So we're going to do 1 factorial over 2 plus, because a summation is always addition, that's why it has the word sum in it, plus 2 factorial over 2 plus 3 factorial over 2 plus 4 factorial over 2 plus 5 factorial over 2. We know to stop now because we reached 5, and that upper bound told us to stop at 5. All right, so that's the same as, so 1 factorial is 1 times 1, so that's like 1/2. 2 factorial is basically 1 factorial times 2, so that's 2/2. 3 factorial is 2 factorial times 3, so that's going to be 6/2. Then we can multiply this by 4 to get 4 factorial, which is what, 24 over 2, and then lastly multiply that by 5 to get 120. I had to think about that for a second. 120 over 2. All right, so we know we have like denominators. Add the numerators. We get 153 over 2. All right, that's our sum. In example 4, we're going to go over these two properties of a summation first. We're going to use them both in this example to evaluate it. So there's two things we need to know. One is that if you have a multiplier in front of like a function, for example, in your summation, what you could do is you could actually do the sum and then multiply by it last. So for example, the one we just did, if we had thought of this as 1/2 times n factorial, we could have done it in the order we did, or what we could have done is we could have pulled 1/2 out of that and then done the sum of n factorial from n equals 1 to n equals 5, and at the end multiplied by 1/2. Because when we do that, we're going to get 153, and at the end 1/2 of 153 is still 153 over 2. All right, so that's all that's saying, is that if you've got a multiplier, and I'm believing the C here is standing for like a constant. So if you have a constant in front of your variable expressions, you can factor it out and then apply it at the end. Really, that's just the distributive property. When you think about it, you're just undistributing that constant. All right, this other property is when you have two things being either added or subtracted. So you could either add them and then find their sum, or you could break it up into two different summations and do the sum of one and the sum of the other. So we're going to do that for this one. We're going to break this one down twice. So I notice that this is a difference here. I have 3k squared minus k. So what I could do first is I could write this as the summation from when k equals 1 to where k equals 4 of 3k squared minus the summation of where k equals 1 to where k equals 4 of k. So we could start it off like that. Now we're going to use this other property, and we're going to actually pull this 3 out. So I could factor the 3 from this one and put it in front of the sum. The benefit to doing this is it's just going to make some of the math here we do a little easier for this particular example, that is. So 3 times our summation, so we're going to have from k equals 1 to 4 of k squared, because we factored that 3 out, undistributed it, if you will, minus, let's see, from where k equals 1 to 4, just k. All right, so now, sorry, that's the bell ringing. We're almost done with this example. So I'm going to basically multiply 3 times 1 squared plus 2 squared plus 3 squared plus 4 squared. And I'm going to stop. So remember, we're adding because that's what we do in our summation. We go from where k is 1 and we stop when k is 4. I'm going to subtract from that, from where k is 1 plus k is 2 plus k is 3 plus k is 4, stop at 4. All right, so now I can go ahead and square these numbers. So 3 times 1 plus 4 plus 9 plus 16 minus the sum 1 plus 2 plus 3 plus 4. So that's 10. And then if we add these all up, we should get 30. So 3 times 30 minus 10. All right, follow the order of operations. 3 times 30 is 90. 90 minus 10 is 80. That is what we get. That is the value of that summation.